Okay, so in this video I'm going to look at problem 93 from chapter 25. So here we are given the cross section of a portion of wire increased uniformly as shown in figure 2539. So let me try to reproduce the figure here. This is a truncated cone, like so. On this side the diameter is A, on this side the diameter is B, and the length of the cone, the truncated cone, is L. The diameter at one is A, the other B, and the total length N. If the material has resistivity ρ, determine the resistance R between two ends in terms of A, B, L, and ρ. Assume that the current flows uniformly through each section and that the taper is small, that is B minus A is much smaller than L. So this has resistivity ρ, and the taper is small, so B minus A is much less than L. Okay. And we are looking at the resistance as the current flows this way. It's along the so this is like a wire, but the wire's thickness changes as you move from one point to the other. Anything else? We are going to assume that the current flows uniformly through each section, and this of course depends on this. If the taper wasn't small, if it was changing abruptly, you wouldn't expect this. You would the current will not flow uniformly, and that will lead to a different arrangement for the resistance. Now, how would you approach this problem? Now, this is similar to one of the other suggested problems, problem 30. So there I mentioned that this immediately suggests that you need to be using this formula, L over A, but is this formula directly applicable? Now the resistivity is uniform through this, so that is fine. The length is okay, right? So there is some length, but the area of this resistor is not well defined. Right? Here the area is pi times A over 2 squared. On the other side, the area is going to be pi times B over 2 squared. So you can't really directly apply this formula. What then you need to do is to divide this into little parts where you can actually apply this formula. And the most natural way to divide this into little parts is to take this into little circular discs, okay, of radius r. This wasn't a good choice, right? I'm gonna just this way, and this is radius r. Okay, so this r is going to change from A over 2 to B over 2 as you move from this side to the other side. And for each of these discs that is going to have some thickness, let's say dl, we are going to have some resistance dr, and that dr is going to be ρ times dl by pi r squared. Okay. Now, as the current flows through this, the same current is going to flow through all of these little resistors. So those resistors are connected in series, which means that the total resistance of this resistive element is going to be just the sum of those resistors. This is the sum of infinitesimal elements, so that's going to turn into an integral. Okay. If this was some other configuration, perhaps we won't be able to argue this, but here they have the same current. Common current means series connection. Okay, so let's write this down. So I can take ρ out, and it's going to be dl by pi r squared. I can take pi out, but I can't take r squared out because r is going to change as I go from here to here. Now, how can I turn this into something that I can actually integrate? So let's choose some coordinate system. Let's say that this is x, this is y, and this one corresponds to x equals 0, this one corresponds to x equals L. So this is going to be ρ over pi x equals 0 to x equals L. This dl is just going to be dx. Okay, it's our incremental element in direction of travel as we sweep from this end to the other end. That dl corresponds to dx. So this dx divided by r squared. Now this r does depend on where we are. Okay? So this radius is going to depend on your coordinate x, so I can take it out of the integral. But I need to write an expression, so I can actually take this integral. Either I have to express x in terms of r, or express r in terms of x. I will choose to express r in terms of x, but perhaps the other one is easier. I'm not really sure, but I will just proceed that way. So let me erase this part. Now this r as a function of x is going to be a linear function of x. It's just going to increase linearly because, well, it's a straight line. In fact, this is the line that I'm looking for. So this r is some a x r plus b. Okay? So at x equals 0, at x equals 0, the r is a over 2. So r at x equals 0 is a over 2. And likewise, r at x equals L is b over 2. Okay? Now this condition, that r is x equals 0, can easily be exploited. So if x is equal to 0, this term drops out. This capital B must be a over 2. So this is a times x plus a over 2. And then I can substitute the value of L over there. And I'm going to have b over 2, the value of r, is equal to L times, a times L plus a over 2, and from this I can find that a is equal to b minus a over 2L. Okay? So I just took this and substituted this condition. I substituted L in place of x and b over 2 in place of r, giving me this equation. I solve it for a, I get this answer. Now I can substitute it over here. So this is going to be b minus a over 2L times x plus a over 2. Okay? Now you need to substitute this over here and take the integral. But so that's not a very hard integral to take. I think first you need to make a substitution of variables to get rid of this a over 2 in the denominator, and then it's a simple integral of r squared. But we are given this condition that b minus a is much smaller than L. So that will kind of kill this, but then we lose all dependence on b, so we can't really use it here. Yeah, I think you just need to take this tedious integral. It is straightforward, but it's going to take some time to work through this. And I'm not going to do it in this video. But I'm looking at if we can use this somehow. As I said, you should not, because of this approximation, drop this out. Then all your dependence on b is going to go away. That will correspond to taking like a cylinder that has no taper. And yes, so you can actually make a Taylor expansion of this. It is a little bit tedious, so I'm not going to do that either. But what you can do is you can write it this way: x equals 0, x equals L dx. So this is b minus a over 2L x plus a over 2 to minus second power. Okay? Now, this is a small number. We know this. This is a finite number. A is large with respect to this one. So what we can do is we can divide everything out by a over 2 and turn this into an expression that looks like 1 plus a small number. Okay? And then with 1 plus a small number, you can use the binomial expansion. 1 plus x to the n is approximately 1 plus n times x, if absolute value of x is much smaller than 1. So you can use that to actually get the integral a bit easier. But still, it's going to be tedious, so I'm not going to go through this either. And in an exam, of course, you have to go through this if such a question is asked. So it's a good exercise for you to do, but it's nothing related to physics, it's purely mathematics. And you either take it honestly by direct substitution, or you make, as I said, and to do it honestly, you make a substitution of variables, you shift this x such that this actually goes away, then the integral gets simpler. Or you carry out the Taylor expansion, the binomial expansion, and try to solve the simpler linear integral.